Welcome to the Explainer. Today, we're going to crack the code, the secret language every single computer uses. You know, it's a language with just two symbols, but somehow it runs our entire digital world. So, how does it work? Let's dive in. All right, let's jump right in with a little puzzle. This one really gets to the heart of the huge difference between how we think and how a computer, well, thinks. It's kind of like a tale of two completely different languages. So let me ask you something. When you type a number on your keyboard, what does the computer actually see? I mean, what's really going on under the hood? The answer? Well, it's probably not what you think. Okay, look at this. The number 22. For us, this is easy, right? We see a 2 and another 2. And our brain just goes, yep, that's 22. Simple, familiar. We don't even have to think about it. But for a computer, it sees this. A string of ones and zeros. I mean, it just looks like a jumble of numbers, right? But here's the crazy part. That jumble, 10110, means the exact same thing as our 22. So how is that even possible? I mean, how can two totally different looking numbers represent the exact same value? Well, the answer to that little mystery, it all boils down to one single, really powerful idea. And that secret is something called the base. To get how computers talk, we've actually got to take a closer look at the hidden rules of the number system we use every single day. So what is a base? It's super simple, really. It's just the number of unique digits a system has to work with. That's it. That's the key to this whole thing. It's like asking how many different symbols are in your counting alphabet. The system we all use without thinking is called decimal, and it's base 10. And why base 10? Well, because we have 10 digits to play with, 0 all the way up to 9. It feels totally natural, probably because, we've got 10 fingers. Once we count up to 9, we're out of symbols. So what do? We just add a new column and start over at 10. Okay, and this is absolutely the most important part. A digit's value isn't just the digit itself. It's all about its position. Think about it. A 2 in the first spot just means 2, but a 2 in the next spot over means 20. Getting this idea that position changes everything is the secret to translating between any number system. All right, so we've got the key now, right? This whole concept of a base. Let's use it to unlock the languages that computers actually speak. And you'll see it's a world built completely on just zeros and ones. So this chart here lays out the main languages in the computer world. You've got our good old base 10 decimal, then you've got binary, which is base 2. That's the computer's native language. And then you see these other two, octal and hexadecimal. You can just think of them as useful shorthands. See, binary numbers can get super long, so programmers use base 8 and base 16 to write them in a way that's way more compact and easier for a human to read. But the most fundamental one, the one that's at the absolute heart of everything digital, is binary. It's base 2. And why just 2 digits? Because it's the easiest, most reliable way to represent something with electricity. A circuit is either on, which we call a 1, or it's off, and that's a 0. That simple on-off switch is literally the bedrock of all modern computing. But here's the thing. Even in a string of zeros and ones, just like in our system, position is everything. Not all of these bits are created equal. The one with the biggest impact, the one that holds the most value, we call that the most significant bit, or, MSB for short. And it's always the one all the way on the left. That's the bit that makes the biggest dent in the number's final value. Then, on the total opposite end, you've got the bit that makes the smallest difference, the one with the least amount of weight. Yup, that's the least significant bit, or LSB, and it's always sitting there on the far right. You can think of it like the ones column in our system. It's the one that makes those tiny, fine-tuned adjustments to the number. Okay, let's put all these pieces together and finally solve our puzzle from the beginning. How do we actually translate our number, 22, into the computer's language, 10110? So there's no real magic to this translation. It's actually a pretty simple mechanical process. All you do is keep dividing your number by 2, and you just write down the remainder each time. It's going to be a 0 or a 1. And you just keep doing that until you can't divide anymore. And here it is. This is the aha moment where it all clicks into place. Just look at the process. We take 22, divide by 2. Take that result, 11, divide by 2. We keep going, collecting those remainders. Then, and this is the trick, you read those remainders from the bottom to the top. And what do you get? 10110. Perfect. And the reason this weird bottom-up thing works is that the very last remainder you calculate is actually the value for the biggest position, that most significant bit. And just like that, the mystery is solved. Okay, so that's a pretty cool trick, but so what? Why does any of this actually matter? I mean, why should you care about these different ways of counting numbers? Because this hidden language is quite literally running our entire digital world. Binary, that's the basic on-off logic inside every single computer processor. Octal, that's still used for things like file permissions on systems like Linux and Mac OS. And hexadecimal, well, it's used to define the millions of different colors you're looking at on this screen right now. It's a really incredible idea when you stop and think about it, isn't it? Every video you stream, every text you send, every crazy complex calculation, all of it at the very bottom boils down to this incredibly simple, elegant system of tiny switches being either on or off. And that kind of leaves us with a final question to chew on. If the entire complexity of our digital lives can be built from a rule as simple as on or off, what other incredibly complex systems in our lives are built on surprisingly simple rules, just hiding in plain sight?